So I remind you what we do when we do tomography. We have a field in the cavity with one atom. We put a coherent field with one atom. We prepare a Schrödinger cat, which is plus or minus depending upon the detections that we get, atom in E or in G. Then we translate this field in the Fresnel plane by adding, homodyning it, adding a coherent state. And then we perform on the displaced field, we perform a measurement of the photon number. So we get, ideally, we get all the PNs, diagonal values of the translated field. And we do that for many, many translations. For each translation, you need to detect a lot of atoms and to change also, to do all the tricks that I used last week. You have to change the phase of the relative phase of the phase shift per photon has to be changed. At the end, after many, many measurements, you get all the information from your computer to reconstruct the linear function. There are a lot of tricks that I don't have time to discuss, but I will show you the final result. This is a kind of, this is an experimental trace. This is the kind of linear function that you get. You see that you have two peaks, the two Gaussian peaks, and in between, if you project on the Fresnel plane, you have positive and negative fringes. Blue means negative. So you see that these interferences here are the signature of a quantum state. And in this case, the square of the distance here in Fresnel plane corresponds to 7.5 photons. Here, the same cut, but with the opposite. This is with a plus sign between the two peaks. This is with a minus sign between the two peaks. So the cut looks very much alike. The only thing which changed is the sign of the interference term. This is with 7 photons. You can do it with a larger field. If the field is larger, you see the two peaks are separated by a larger distance, and the fringes are closer to each other. So you see the kind of result that we get. I show you the figures that we published in the paper is shown here. It's the same thing. You see here, again, the two Gaussian peaks. The quantum interference is given by these terms here. This is the experiment. This is the theory. What you should get if there were no noise in the theory. This is a Schrödinger cat reconstructed when you detect the atom in state G. And this is what you get if you detect the atom in state E. So you have to be careful. In fact, in this experiment, you have to separate the data corresponding to the atom detected in one state or in the other. If you don't separate the data, you get a statistical mixture of the two results, which we can get from our experiment. And then you get just the two Gaussian peaks, and you have erased the fringes, which have opposite signs here and here. So this gives you all the information you want. And you see that in order to get this, you have to make, it's not enough to detect one atom. You have to detect one atom and then many other atoms too, which will tell you what the first atom has done to the field in the cavity. And this experiment takes a very long time. In fact, just to get one of these kind of radiography of the field, it's about 1 day of taking data with about 10 cycles per second. You cannot go faster because the field decays in 1/10 of a second in the cavity. So you have to let the field decay, and to get it to decay faster, you have to use these vacuum cleaner atoms in between, but you cannot go much faster than that. We can also reconstruct Fock state, photon number state. I remind you last week that we can, I told you last week how you can prepare photon number state in the cavity. You can do it either by a measurement, so you measure and you find a given photon number, or you can do it in a deterministic way by filtering from a coherent state with a measuring independent light shift. Once you have a Fock state, you can do exactly the same procedure to measure the density matrix. And you see here, these are the density matrix of n equals 0, n equals 1, n equals 2, n equals 3, n equals 4. For n equals 4, you see you have some noise. You find a peak corresponding to n equals 3. Why? Because during the time you make the measurement, the field has a time to decay from 4 to 3. And so you get a mixture on 4 and 3. The larger the photon number, the faster the state decays. So you cannot go much higher. This is the density matrix, but you can take compute the Wigner function, and you see that the experimental Wigner function looks very much like the one I showed to you before. It is n equals 0, n equals 1, n equals 2, n equals 3, n equals 4. You see these rings, the number of rings increases. You see also that n equals 1 has a negative peak at origin, n equals 2 is positive at origin, n equals 3 is negative at origin, n equals 4 is positive at origin. So you can reconstruct all the Fock states, and all these ripples are quantum features of Fock states. The fact that you cannot interpret this as a probability because the Wigner function takes negative values. So now let's look at decoherence. You see these pictures here show snapshots of the Wigner function as a function of the delay between the preparation of the cat state and the time at which you make the measurement of the Wigner function. So now you have another dimension that you have to take into account. You have to let your Schrödinger cat for some time and measure after a delay. And you see that indeed, if you take this kind of snapshots, you see that the fringes disappear. And also another effect which occurs that the two peaks get closer to the origin. The fact that the peaks get closer to the origin is just a classical relaxation of the field which goes to vacuum. But in fact, you see that these ripples decay much faster than the energy. And this is decoherence. Decoherence occurs much faster than the lifetime of the coherent states themselves. So in order to, this is of course experimental, but I will start by giving you very briefly the theory, how you can understand theoretically what's going on. And the theory was made about in the 1980s by Wojciech Zurek, the American physicist who published in 1991 a very well-cited paper in Physics Today, kind of semi-popular paper in which he describes the decoherence of this kind of cat state. So you see what happens is that the photons keep bouncing between the mirrors, and there are some imperfections. So sometimes a photon is scattered out, or sometimes a photon is absorbed by electrons in the mirrors. And you can model this by assuming that the environment is made of a very large number of modes in the environment, which at the beginning of the experiment are all in vacuum. And when the field is leaking due to imperfections, these modes get filled by photons. And you get some information about the field inside because the energy is leaking out. So let's build this model and see how it works. We start with a coherent field, alpha, and we start with all the modes in the environment in vacuum. So we have a product of which is unentangled of alpha and all the mode in vacuum. What will happen, what we know about the coherent state, we know that it decays exponentially. So the coherent state will have its amplitude decaying exponentially towards vacuum with a constant kappa over 2, where the factor 2 is inside the exponent, where kappa is the decay of the energy. The amplitude decays with the rate kappa over 2 for the energy to decay with the rate kappa. And each mode of the field will have a very small coherent field building up. And we have to take the product of all these small components in the different modes I of the environment. And I have a conservation law, which is obvious. It is clear that the energy which is going in the environment, which is the sum over I of all this epsilon I squared, has to be equal to the decrease of the energy in the field mode, which is alpha squared times 1 minus E minus kappa tau. And alpha square is just the average photon number in the coherent state. So you get this identity. The sum over I of all the small intensities, the square of the amplitude in all these modes, has to be equal to the average photon number times 1 minus E minus kappa tau. This is just conservation of energy at time t. Now, what we have to do is just to apply the rules of quantum physics, the superposition principle. If you start not with alpha, but with a superposition of alpha and beta, alpha will decay. And again, the factor 2 is inside the exponent here. Time, you will have here the state of the environment plus beta times the state of the environment corresponding to the component beta. And what the E alpha is just the product of all the modes with E epsilon I alpha t, and epsilon beta is the same with beta replacing alpha. So that's just the superposition principle. And now what we have to look at is what is this state? What is the density operator of this state? And now we have to trace over the environment because we want to see what happens to the field in the cavity. So we have to take the trace of this quantity over the environment. And when we do that, we get the density matrix for the field. We have the diagonal elements are just the one corresponding to the projector on alpha and beta. And the off-diagonal elements are have here the ket alpha bra beta or ket beta bra alpha multiplied by the scalar product of E beta with E alpha or E alpha with E beta. This is just the operation of tracing, not looking at the environment, looking just at the system. And now what we have to do is to express this knowing that alpha is equal to alpha naught EI delta phi, beta is alpha naught E minus I delta phi. And so the small field in the environment are epsilon naught E plus or minus I delta phi. And it's a linear coupling. The amplitude in the environment is proportional to the amplitude of the field, and the phase is the same because it's just a linear coupling of the field in the mode with the environment. And look at this quantity here. We have to look at the scalar product of epsilon naught E minus I delta phi with epsilon naught E plus I delta phi. And I have represented here the representation of this field. They are very small fields. In each mode, epsilon has a very small amplitude. And I remind you that the uncertainty is just a blob of radius 1. So you see that these two fields overlap a lot with each other. And you can replace this by the expansion is just 1 minus 2 epsilon naught square sine square delta phi, which is a very small quantity. So you see that the information that you get in each of these modes is very small because they overlap a lot. But you have a lot of modes. And what we have to do is, of course, to take the product of all these quantities which are very close to 1. And when you do that, you see what the overlap of the two states of the environment is just the product of these quantities. And of course, the product of an exponential is the exponential of the sum. And you get finally exponential minus 2 times sigma I EI square sine square delta phi. This is just the result of what you have above. And now we are taking a lot of product of quantities which are smaller than 1. And this product becomes very quickly very small. What you have to do now is to remember that you have conservation of energy. And this quantity is equal to this. This is a quantity that I have written on the previous slide. It's exponential minus 2 n bar 1 minus E minus kat tau sine square delta phi. This is just the conservation of energy from here to here. And now you expand this at a time very short compared to 1/k, because decoherence would occur in a time very short compared to the damping time of the energy. And when you do that, you replace E minus kappa tau by 1 minus kappa tau. You get this quantity here, and you see that you have a decay of the coherence which is proportional to the photon number. You have a decay rate proportional to the photon number, and this is the important feature here. So what you have to understand is that each environmental mode have a very small information, but since you have a huge number of modes, when you multiply 1 minus epsilon to a very high power, you get very quickly 0. And you get 0 at a rate which is proportional to the photon number, which appears in this expression. So I summarize all this on the next slide. If you have the two components like this, the distance between the two components is 2 square root of n sine delta phi. It's just Pythagorean theorem, or just a very simple property of the triangle. And the quantity, the contrast of the fringes, the contrast of the off-diagonal, the amplitude of the off-diagonal element is given by this expression, which is just proportional to minus d square over 2tc. Kappa is equal to 1 over tc. So you get this expression where the decoherence time is just 2tc over d squared. So the decoherence time is the decay time of the energy divided by the square of the distance in the Fresnel plane. So it's just a direct consequence of the previous expression. So you see that the field, in fact, in the cavity decays with 2 time constant. You have if you start with a Schrödinger cat with a lot of fringes in between, very quickly, before the system has time to, before the coherent state have time to decay, the fringes disappear. And after that, the two coherent states decay slowly toward the vacuum. And I will show you on the next slide, I show you a picture of that, which is an experimental realization. What we take snapshots with an increasing delay. And you will see the time constant here. We start after 1.3 milliseconds. And from that time on, you will see what happens as a function of time. I remind you that the damping time of the cavity field is 130 milliseconds. So the decoherence will occur about time scale about 10 times shorter. So we have to look at what happens during the first 10, 20 milliseconds. Then you will see that all these fringes will have disappeared, while these two peaks will still be far away from each other. So let's look.
You need to detect the atom, right? Which is the state of the atom.
But for this, you need to detect a lot of atoms to reconstruct the linear function.
And the lifetime of that is much longer. The lifetime of the atom in the state.
Yes, the atom, in fact, what counts is the time it takes for the atom to go across the cavity, which is very short, which is 100 microseconds, which is much shorter than the lifetime of the atom. The atom is just used, you have a string of atoms which is used to reconstruct this function. And you have to reconstruct it at different delays. So this takes even much longer. It takes several hours to get one snapshot, and then you have to do it with a longer delay. So it takes days to get the movie that I will show you now. So look at what happened. Excuse me, I have to come back. Yes, I have to do that here. So you see the fringes, we are now after 7, 8, after 10 milliseconds, you don't see, there is some noise, but you see the fringes have disappeared. And now we have a statistical mixture of the two states. And I will stop about after something like 40, I think it stops about 49 milliseconds. So after this time, the two peaks are a little bit closer, but they are still well separated. So let's do it again. So it's not perfect. You have noise, of course, but you see that the disappearance of the interferences is much faster than the dissipation of the energy. And we have made a quantitative analysis on the next slide. You see here the exponential decay of the even and odd cut, and the lifetime that we measure is about 17 plus or minus 3 milliseconds, whereas the theory gives 22. So we have to explain the discrepancy. It decays a little bit faster than what is expected from the model I gave you. The main reason is that we have a little bit of thermal field. We have the probability to have a thermal photon in the cavity is 5%. So the theory has to be corrected by that. And the correction has been made in the paper that I quoted at the bottom. So you see in the presence of a little bit of thermal field with a probability of an average number of thermal photons of 0.05, then you find a decrease of about 13%, and you find that you expect 19 and you find 17. And we did that for different size of the cut, and of course this is when there is a good agreement between the theory and the experiment. So you see, you can really observe what happens to this superposition as a function of time. Of course, for that, you need to have a large ensemble. So in the end, what you find is that very quickly, the cat is a probability of 50% alive and 50% dead. What does it mean? In fact, since we are doing a measurement on an ensemble, we can only get the probability for the two outcomes. But for each outcome, if you were able to measure your state, you would be in one coherent state or in the other, of course, and the cat would be either dead or alive. So the point, let me go on. You can explain that in different ways. The kind of, let's consider the cat when you have delta phi equal to plus or minus pi over 2. This is a case where the two fields have opposite phases. What I have shown to you before is that you do not need to have opposite phases. As soon as you have two coherent components, this formula applies. But assume you have opposite phases. In this case, it is easy to find out that the plus cat has only even photon numbers, and the odd cat has only odd photon numbers in its superposition, because I remind you that the amplitude to have n photon is alpha to the n. So if you are in the even cat, alpha plus minus alpha, then you suppress the odd numbers. If you are in alpha minus alpha, then you suppress the even number. So the photon number parity is different for the even cat has even photon numbers and the odd cat has odd photon numbers. This means that in fact, the even and odd cats are eigenstates of the parity operator. And the parity operator can be written in a very simple way. The parity operator is just E minus I pi A dagger A. If A dagger A is equal to n, you get E minus I pi n, which is plus or minus 1, depending upon the parity of n. So in fact, you have this identity P acting on the plus cat give you the plus cat, P acting on the minus cat give you minus the cat. Now, I remind you that last week, what we showed is that if you have a pi over 2 shift, what the atom does is to measure the parity of the photon number. You get the same, you get the atom in level E if the photon number is even, 0, 2, 4, and you get the atom in level G if the number of photons is odd, 1, 3, 5. So now you see that you have another way to interpret this experiment in the case of a pi over 2 shift of photon. What you can say is that the atom which prepares the cat is in fact measuring the parity of a coherent state. So you have a coherent state, you want to know the parity. If you find an even parity of prepared alpha plus minus alpha, you find an odd parity of prepared alpha minus alpha. And it is very simple. It just comes from the fact that a coherent state is a superposition, of course, of the even and odd cat. So you start from a coherent state and you project it either on an even cat or on an odd cat when you detect it in E or G. This is another way to look at the experiment, but it's exactly the same. Now, what I will show you here is another aspect of this experiment, which is the fact that when you count the photons in the way I described last week, you erase information about the phase. Look at what happens. You start from a coherent field, which has a photon number distribution. The coherent field is a blob here. And the first atom, you send an atom which has a pi/2 shift per photon, which produce a pi, which dephase the atom by pi. So what does this atom do? When it crosses the cavity, suppress one out of 2 photon numbers, and now you get a Schrödinger cat. So you see that you have lost some information about the photon number. You have gained some information about the photon number. You know that there is no 1, 3, 5 photon, and you have lost some information about the phase. Instead of 1 phase, you have 2 phases. Then you send a second atom with a pi/2 phase shift per photon. So you decimate another photon number here, but now you have 4 phases because each of these phases is split into 2. The third atom will leave only 1 photon number, and now you have lost information about the phase. So you see that there is a complementarity between photon number information and phase information. When you go from a coherent state, which is a not well-defined photon number, but a well-defined phase, you end up, after a few atoms, into a state which has a well-defined photon number, but a phase completely distributed around 2 pi. And this is, again, an illustration of the complementarity between photon number and phase. On this slide, I take advantage of another property of the coherent state, which I have not discussed before, the fact that a coherent state is in fact an eigenstate of the annihilation operator. You see, if you take the annihilation operator acting on beta, you have to remember that A acting on n gives you square root of n minus 1. So when you rewrite this expression, you find that A acting on beta gives you beta times beta. Because this expression here is again give you beta because you have just sent n into n minus 1 and you sum over all the n values. So the coherent state is an eigenstate of the annihilation operator with an eigenvalue, which is the amplitude of the coherent state. And it's no longer a real number because A is not an emission operator, but it's still an eigenstate of this operator. So what does it mean? It means that if you have A acting on a cat state, A acting on beta plus minus beta will give you beta minus minus beta. So A acting on the plus cat gives you the minus cat. And what does it mean, A acting on the cat? A is the operator which destroys a photon. It means that if you destroy a photon on the plus cat, you get the minus cat. And this is obvious because the plus cat has only even photon numbers. If you destroy an even photon number, you will get an odd photon number. So you see that each time you lose a photon, the cat jumps from even to odd, and so on. So this will give you another view of decoherence, another interpretation of decoherence. Suppose that you have an even cat. And at some point, you will lose a photon. And the first photon will be lost at a rate which is inversely proportional to the photon number. If you have a huge photon number, it will take a very short time to lose the first photon. But as soon as you would have lost the first photon, the cat will jump from even to odd. And since you don't know when it happens, it means that after a very short time, you have a mixture of even and odd cats. And it takes a time which is inversely proportional to the photon number before you are in a situation where you are in a mixture of even and odd cats. And this again shows you that the decoherence time is 1/n. It's inversely proportional to the photon number, because very quickly you will lose the parity information because of the loss of photons. So it's another view, another interpretation. And I want to conclude that very briefly by telling you that this explains why with macroscopic objects, you never see this kind of thing, because as soon as you have a huge number of quanta in the system, it becomes very hard to keep track of all the quanta in the system to keep the coherence. Let's go back to the story of Schrödinger. If you take just look at some orders of magnitude, you take a cat, which is made of something like 10 to the 27 or 10 to the 8 atoms. So you have a huge number of quanta in the system. Take the lifetime of a cat, let's say 10 years, 1 billion seconds. It's only 10 to the 9 seconds. If you divide 10 to the 9 second by 10 to the 27 quanta, you get decoherence time, which is of the order 10 minus 20 seconds. And I challenge anyone to kill a cat in a time shorter than 10 minus 20 seconds. That doesn't make any sense. The cat is in a statistical mixture even before you start the experiment, because it's coupled to the environment. A living animal cannot be considered as a pure state because it is coupled. The cat needs molecules around him to breathe. It needs thermal photons not to be frozen out. So it's a system which is open. And an open system is represented by a density matrix from the beginning. It is entangled with the environment from the beginning. So this experiment has no meaning for that. And if you want to protect systems, you have to put them in an environment where you have, for example, a cavity at very low temperature. Make sure that you have no losses in the environment. And this is a big challenge of all quantum information science. If you want to build a quantum computer, what you want to have is a kind of big Schrödinger cat doing computation, keeping the coherence and keeping the entanglement. And as soon as the system becomes large, it becomes exceedingly difficult to do. Okay, so this leads me to in the last 10, 15 minutes, I just want to, in a few words, to just tell you that the Cavity QED experiment that I showed to you, described to you here, Rydberg atoms in microwave cavity is not the only domain in this field. You have a lot of beautiful experiments which have been done with different setups. For instance, you have cold atom in optical cavities. You can build small cavities with mirrors very close to each other, a distance of less than 1 millimeter, and send slow atoms, cold atoms across it, or trap cold atoms in these structures. And there are beautiful experiments which have been made in the optical domain, Cavity QED. You can also have atoms coupled to optical microresonator. You can have, for example, a small sphere and have a beam of light going around the sphere with an evanescent wave outside. And so it's a microresonator, and it's called a whispering gallery mode. It's a mode of the field which follows the boundary with a little bit of the field leaking out, and you have atoms grazing the microresonator outside, and you can couple atoms to these modes and do also beautiful experiments. You can also have quantum dots in band gap materials. A quantum dot is a kind of nanostructure in which electrons have energy levels, which can, it's a kind of box in which the electrons have quantized levels. They can emit or absorb light. And if you put them in a layered structure like that, this structure by Bragg diffraction plays a role of mirrors, and you can have a kind of Cavity QED system. And the last system I want to stress is called Circuit QED. In Circuit QED, you have artificial atoms, and I will say a few words about that, which are embedded in a coaxial line, for instance, in which act like a microwave resonator. It's a kind of, you have a strip line in which you can trap microwaves, and these microwaves can be coupled to an artificial atom, which is a Josephson junction in an electrical circuit. This is called Circuit QED, It's a very active, it has been for the last 20 years, a very active field. There are a lot of experiments which have been performed in different labs in the US and in Europe and in Japan. And these two systems have very strong similarities. In both cases, you couple a two-level system to a mode of the field, but in different regimes. And as I will show you now, the experiments are very, very similar to the one I have described to you. I just give you a glimpse of what can be done by looking at an experiment which have been done by the group of Martinez in Santa Barbara in the US. There is an artificial, the difference is that it's in solid state physics, and the atom is an artificial structure, which is here, it's about 1 millimeter inside. There is a printed circuit here. It's a superconducting circuit, and this circuit has quantized energy levels. I will come back to this in a moment. And it is coupled through a capacitance to a strip line here, which is a coaxial line which plays the role of the cavity. You have a standing microwave in this cavity. You can feed microwaves. You can use a microwave to manipulate the qubit here. This is what we do in our zones R1 and R2 in our experiment, pulse of microwaves. And you can also inject microwaves in the resonator, which is what we do when we shine line on the side, shed line on the side. And you can detect the qubit here by a detector called the SQUID, a superconducting quantum interference device. A few words about the artificial atom. This artificial atom is the main element is what is called a Josephson junction. You have two superconductors, two superconducting islands, which are separated by a very thin piece of dielectric insulator. And the electrons in the two islands, these are superconducting pairs of electrons, which have a phase, delta 1 and delta 2. And there is a phase difference between the two. And Josephson effect says that when you have a phase difference, you have a current going through the gap. And the phase difference plays a role of the position. And you have a potential which depends upon the phase difference. So the system behaves as a kind of particle which has quantum energy levels. The phase playing the role of the position, and the photon number, the pairs number difference between the two parts playing the role of the momentum. And you have an uncertainty relation between position and momentum. The important point here is that this potential is anharmonic. That is, the separation between 0 and 1 state is different from the separation from the 1 to 2 state, which means that if you use a microwave, which is resonant with a 0-1 transition, you have a two-level system, and you can forget about the other levels. So the people working in this domain during the last 20 years have been able to show that you can build these artificial atoms, you can manipulate them with microwaves, you can give them long lifetimes, and you can do the same kind of experiment that we did in Cavity QED with this system. And I will just give you a few examples here. How can you pump photons into your microwave cavity? You start, so it's exactly the same energy levels as the one I have shown to you before. So if the atom is if the artificial atom is in the lower state, you have the state G0, G1, G2. If it is in the upper state, you have E0, E1, E2. And you can tune the atom out of resonance with the cavity. So you have a gap here, and you apply a microwave pulse, which brings you from G to E. So what you have done here is that you have pumped energy into the artificial atom. Then you change the frequency of the artificial atom and you put it in resonance with the cavity. So you get this situation. And in this case, the system will evolve from E0 to G1. It will be a resonant interaction, and you wait for exactly the time required, a pi-Rabi flop. And so you have pumped one photon inside your resonator. Then what you do is that you shift out of resonance your artificial atom, and you apply to the atom, which is no longer resonant to the cavity, another pi pulse. And so you climb here, and then you put them back in resonance. And now you have Rabi oscillation from E1 to G2, and you wait the exact time required to go to G2. You make another pi Rabi flop, which is shorter because the coupling is larger by ratio square root of 2. So you see that by manipulating the frequency of these artificial atoms that you can change by sending a flux into a magnetic flux into your superconducting junction, you can pump successively larger and larger photon numbers into your artificial atoms. And how do you check that you have prepared a Fock state? You do exactly in the same way as I described you last week. Once you are in a given Fock state, you just let the Rabi oscillation occur for some time, and you get a beautiful Rabi oscillation signal, which has a frequency which increases when n is going from 1 to 2 to 3 to 4 to 5 to 6. So you see that you can have pure Rabi oscillation, which tells you that you have a well-defined photon number in the cavity. And this looks very much like what I have shown to you last week. We can do that in Cavity QED also. You can prepare deterministically 0, 1, 2, 3 photon. Another experiment which has been done in both cases. Last week, I showed you that we can, by doing microwave spectroscopy of atoms into a cavity field containing a coherent state, we can separate the different photon numbers. We can take the spectrum of the microwave spectrum, which gives you the signal corresponding to 1, 2, 3 photons. And they do exactly the same thing in Circuit QED. And you see that you can separate the photon number. But you see there is a big difference in orders of magnitude. In our case, it's about 10 kilohertz per photon. Here, it's 10 megahertz per photon. Why? This is because the coupling they have is much stronger. The artificial atom has a size which is about 1,000 times larger than our Rydberg atom. Rydberg atoms have an electric dipole of 0.1 micrometer, and these artificial atoms have a dipole of 100 micrometer, 1/10 of a millimeter. So it's increased the frequency by 3 orders of magnitude, which means that all these Rabi flops occur 3 orders of magnitude faster. So they can do a lot of, it's the dynamics and the speed at which they can do their operation is 3 orders of magnitude faster than in Rydberg atom Cavity QED. They have also prepared Fock states. You see, these are the Fock states in Cavity QED. And at the bottom, you see the Fock state for n equals 7 obtained in Circuit QED. Finally, they have also Schrödinger cats. At the left, you see our cats. On the right, the kind of cat they have in Circuit QED. So I will conclude very briefly. First, I would like to emphasize the differences between Circuit QED and Cavity QED. First of all, the frequency of the radio frequency resonator is about 1 order of magnitude smaller than in our case, which means that they have to be about 1 order of magnitude at a lower temperature. So their superconducting device work around 20 millikelvin, whereas we are working more like around 1 Kelvin, 0.81 Kelvin. So the restriction temperature, the restriction is more strict than ours. This I already said, artificial atoms have much larger sizes than Rydberg atom and the stronger coupling to microwaves. Vacuum Rabi frequencies are 3 orders of magnitude larger in Circuit QED gate, and the gate operation are of course much faster. Another difference, of course, is artificial qubits are scalable. They are imprinted on a board, and so they can use all the technology of condensed matter physics, of solid state physics. Our qubits are flying across the cavity, so it's not very convenient for an application. And of course, their qubits are permanent and they can be reinitialized after being measured. Now, one advantage, theoretical advantage of Rydberg atoms is that they're all the same, whereas their artificial atoms depend upon the exact dimension of their circuit. So when they have several qubits, they have first of all to adjust the frequencies and to make, there is a lot of tuning to be made before they can start their operations. So just on this slide, I want to emphasize the fact that in one way, we can say that all these experiments are realization in the lab of the thought experiments of the time of Einstein and Bohr. It's a kind of photon box that I discussed in one of the lectures, but we have come a long way since then. You see, these experiments have been developed around during the last 20 years. Our Cavity QED experiments were done in the years 2000, and around the year 2010, Circuit QED has caught up with us. They are able to do exactly the same kind of experiment, and they said much faster than what we do. So there is a lot of groups working now in Circuit QED with the goal, the very long term goal to build a quantum computer. And so the artificial atoms are candidates, qubit candidates for building such a computer. They are compete with ion in ion traps, but for the time being, the systems that are operate with a few, at most a few tens of qubits, and it's very far from solving all the problems. There are a lot of problems because one has first to do error correction. We have to keep the coherence of the system, which is not easy. And we have also the problem, the challenge of scaling up this to a huge number of qubits to be able to do something useful. So I will conclude by just trying to emphasize one or two important points about what I have tried to illustrate during these lectures. I want to insist upon the complementarity between fundamental research and applied physics, about the fact that the discoveries have come together, have been made possible by the development of instruments. So you start by observing nature, you build theoretical models, it leads you to predict new effects, for instance, Bose-Einstein condensation or the laser effect. This leads to novel technologies. You build devices which use the new effects that you have, which come from the theoretical models. And these novel technologies allows you to do more precise observation, which are either confirming or falsifying the theories. And so you have a kind of loop, which is a virtuous loop. It's the way physics is working. And in the meantime, the novel technologies give you tools which have revolutionized various fields in physics, chemistry, biology, and medicine. They gave you many examples of that. What is in store in the future? Of course, everybody hopes that we get novel quantum technologies out of these quantum simulators, maybe one day quantum computers. You can use this system to do more precise measurements, quantum metrology. I gave you an example with atomic clocks and what you can do with atomic clocks now. Quantum communication also using entanglement of photons, for instance, in propagating in optical fibers or in free space. You get new tools for exploring the universe. One example are of course, the gravitational wave antennas, which use very stable lasers. And the next generation will be interferometers in space, placing mirrors on satellites and looking at gravitational waves by measuring with extreme precision the position of satellites with respect to each other. Super precise optical clocks will be used to test cosmological theories, and I tell you a few words about that. Maybe some of these devices could try to detect dark matter. Of course, one big question is the unification of quantum physics and general relativity. I don't mean that it's optics which will do that, but what I want to say is that quantum physics and general relativity have come from questions raised by optics. Quantum physics both have come from mysterious puzzles, which at the end of the 19th century could not be explained classically. And it remains today a kind of incompatibility between these two theories. And something has to give up, something has to change. And I think it's also quite revealing to realize that the vocabulary of light comes into play to discuss these things. When you talk about black holes, you say black, it means that no light can escape from it. So there's a property which is related to light. When you talk about dark matter, also it's an adjective which is connected to the fact that these systems don't interact with light. So I don't know what the future is, of course. What we will find in the future, and I just will conclude by a sentence which is attributed to Bohr, but to many other people, that it is hard to make predictions, especially about the future. And I think this is one of the charms of research, that we don't know what we will find in one way or the other. There will be applications, certainly, but maybe some of the applications will surprise us because we cannot think about them today. So we'll stop at this point, and thank you for your attention over these 15 weeks.